Everybody, one last example. It's a fun one. I really enjoyed this example. What do we do next, right? Check this out. Imagine a wooden sphere. We'll say it has a radius of capital R. But then we're going to drill a hole through the center of it. So a cylindrical hole of radius little r drilled through the middle. Kind of cool image there. Can we find a formula for the volume of the wood that is remaining? Yes, we can, using cylindrical shells. Here it is again. A wooden sphere of radius capital R has a cylindrical hole of radius little r drilled through the center. Find a formula for the volume remaining. Here's what I want to do. I'm going to make a drawing of it, and then we'll end up, kind of making a few drawings and laying an XY plane on top. So first, imagine the sphere. Something like that, okay. It has a radius of capital R. Then somebody comes and drills a cylinder out. All right. And this cylinder has a radius, I'll put there at the bottom, a radius of little r. Now, when you drill through, right, it's more than just the cylinder that gets removed, because there was a little bit of a bump on the top of the sphere and on the bottom of the sphere that also got drilled through, right, that you might not think of being as part of the cylinder. If where it hits, there's still going to be a little bump. So rather simple scenario, but it takes some, pretty advanced calculus and the cylindrical shells method to figure out the volume of what's left. Okay, here's what we're going to do. Think of just like a two-dimensional version of what we see there. We're going to put that on an XY plane. So think of a circle of radius capital R. And think about like a piece like this being removed from it. What region could we shade that would, thinking about the solid of revolution, thinking about that region spinning around an axis, what region would it be to create this shape? Right, you think, what would spin around to make that volume? It would be this right here. This region, and just the region on the right side, because it's got to spin all the way around 360. If we took that region right there and spun it around the y-axis, it would create that shape. Right, there'd be that gap in the middle. So maybe we say this is at R, this would be at little r, and we actually don't even need this line at all. You just think of that spinning around, and that gap, right, would be doubled up as it spins. Okay. What do we do with that? Let's think about the equation of that circle. The x squared plus y squared equals capital R squared. Okay. What's going to be useful from this? And it turns out it's going to be the y. If we thought about the radius and the height, I won't draw them yet. I'm actually going to do another drawing in a second, but that height would move vertically. Here, y equals the square root of capital R squared minus x squared. This would be the top half of our circle. What we're going to be able to do because of symmetry, we can think of just this top half of the region spinning around and then double it. Okay, so one more drawing. Let's think of just the top half of the circle. Here's R, here's little r, just this portion. And we'll think about the height and the radius. The height, right, runs parallel to the y-axis. It's a vertical axis, so this is going to be in terms of x. So we got h of x, and then the radius right there, that's r of x. So what is h of x, the height? Well, it's going from the x-axis up to the top of the circle. So it's going to be square root r squared minus x squared. What about r of x? Well, that's just the distance coming off the y-axis. It's so simple that it's often confusing. That is simply x. We're thinking of our point here as being at xy. So the y value is the height, the x value is the radius. Okay, and then we're going to double, because since we're getting away with only doing half of it. Okay, we got it set up. Here we go. Volume is 2 for the doubling times 2 pi. Integral. What are the limits of integration? Well, if you look at the region, there's where we start, there's where we stop. It's from little r to big R. In the end, our formula is going to be in terms of little r and big R. If we know those two, the radius of the sphere and the radius of the cylinder, then we could plug those into our formula. So we'll use little r and big R here. Okay, and then it's radius times height dx. Looks good. Okay, wow. How are we going to integrate that? And it looks like, wow, I don't know what to do, right? It's got this square root, like I can't multiply the x in, you know, take a look at this. The capital R squared, right? That's a constant, whatever it is. Also inside here, we have x squared. The derivative of x squared is 2x, which we could use here. This is a u substitution. We're going to take u to be what's inside the square root, capital R squared minus x squared. Because then du would equal negative 2x dx, right? R is a constant. We can move the negative 1/2 over, and then we've got the rest of it, the x dx is taken care of. Oh. Okay, so the new integral will be b equals, I'm just gonna, let's write that as 4 pi. Okay, integral from little r to big R, square root of u times negative 1/2 du will take care of the x dx. And there's our substitution. From there, I can move the negative 1/2 all the way out. Let's make it negative 2 pi. Integral from little r to big R, and I'll think of square root u as u to the 1/2. then we're really in business. Antiderivative is 2/3 u to the 3/2 from little r to big R. Okay, but then I'll simplify -4π/3, put the u back in. It was capital R squared minus x squared to the 3/2. And we still gotta plug in little r and big R. Looks good. Okay, let's do that. We're almost there. Keep this out front. Let's see what happens. Oh, check this out. When you plug in the big R, it's 0. Plug in the little r for x, and it's r big R squared minus little r squared to the 3/2. So that negative that popped out here is now going to cancel out. And we've got 4π/3 big R squared minus little r squared to the 3/2. There's our formula. Looks good to me. So if we know capital R and we know little r, we could plug those in, and there's the volume of what's left of the original sphere after you drill that hole through the middle. That was a fun problem. Okay, so kind of reflecting, right? Thinking, the first thing we had to do was make a drawing on an XY plane and then shade the region that would then rotate to create the three-dimensional figure that we're looking for. Once we have that all drawn and we note where the little r and big R occur, we did take advantage of symmetry, but we also said, okay, like so now that this is on an XY plane, like what is the equation of that boundary around the outside? Okay, we can solve it for y, and then we can just focus on the top half, do the symmetry thing, multiply by 2 to get the full volume. And there you go. What a cool formula. All right, you guys. That's it for 6.3. It's a good ending.